Hello, I'm S. Milad and hope you had a great day. Let me introduce myself a bit further. I already said my name and I'm 18. I'm going to go to university by the end of this September, and I haven't been to university. I was in high school, and this year I'm going to the university for the first time, so I don't know the math that they teach in universities. Besides, and besides the mathematics that are taught in the YouTube by yourselves or like Three Blue One Brown and other channels that I usually Edivu and some other channels that I usually watch for learning some math. My mathematics are just the experience, just contains the high school mathematics and a little glimpse of the integrals and Fourier series and Taylor series in just in a nutshell, not the whole of it with the integrals and how to calculate them, because no one has taught it in the YouTube. And I live in Tehran, the capital of Iran, and I really enjoy studying physics and electronics, electrical engineering, computer programming, and some mathematics that are relevant to the topics I said, mentioned, like calculus, some kinds of analytic geometry, linear algebra, a little bit of it, not the whole of it, but a glimpse of it that is used in programming. And the my biggest love in these topics in between of all I said is for physics and quantum physics and the new physics that are the modern physics that are introduced about 400 years ago and so on until here up to now, actually. And I wanted to apologize for my accent if I just can't pronounce something well, or if I actually speak with the accent sometimes ununderstandable, or I get some between my speaking. I apologize for that, because it's been 3 years I haven't talked to anybody in English, and this is the first video that I'm recording in English, and the fourth video that I'm recording this way, with recording the screen and recording myself on the screen this way. This is the fourth one, after that those three actually. And let's get started. For starting, I wanted to tell you something interesting and the thing I love about mathematics. The thing is, I very pretty much like when the math has a pattern, like you solve an equation, then a higher degree, then that equation in a higher degree. I'll show you what I mean. And you see something, and there's something going on in there that you can predict what's going to happen. If I could be more specific, I can say, like, let's imagine a system and its behavior. And we know its behavior, it's kind of constant. It doesn't change. The behavior of the system doesn't change. Kind of, actually. No system, we have no system that has a constant behavior. But let's imagine that we have such a thing. if you know how it evolved from the past to the present, you can predict if the behavior is constant, how can it be in the future? And this is really surprising for me, and I think this is the most amazing thing that the math is gifting us with. Let's see some examples on this topic that I said actually. This mess. Let me just clean this mess, and then I'll show you what I mean. There we have this one. Okay, everyone is familiar with a line. This is a line, and this is a line. This is a special line because it actually intercepts with two dots. These two dots are going to determine the equation of this actual line. Yes, line. Where was it? This is the equation. If I get it here, yes, this is the equation. Y equals to a1 times x plus b1, and then it is a1 here, y2 divided by or over x2 minus x1 delta x minus y1 over delta x. And I'm not stupid because I've written this way. I want to show you something that is special about writing it this way, and that is we know it's just so simple. We have a line that can actually be this here. It can just be determined with these two dots. But if we dig in further, we can have we are watching a line that intercepts or contains two dots. So we can have a parabola that contains three dots. So let me show you the third dot. This is the third dot, and this is the parabola. Behind this one, this is the parabola. This parabola has this property to contain these three dots wherever they are. This is just beautiful, and the equation that describes this parabola in particular, this general parabola that contains these three dots, is amazing. I mean, it's horribly amazing because it's a bit undeniably calculationful. But yes, and the thing here describes the dot, and describes the thing here describes the parabola that we're about to see. I mean, we're seeing here. It is y or y equals to a2 times x squared plus b2 times x plus c2. And here's a2, if I don't get it wrong, y3 over this thing, and actually, well, where were we? Oh, here. So this was the equation for the parabola that actually contains three dots, and therefore the a here, the a2, is actually, if I find Yes, A2 is here. This mess actually is A2 that describes how the A relates, the A of that equation I showed you, relates to this parabola here. I mean, this is the A in respect of x1, x2, x3, y1, y2, and y3. And it does a good job of setting the parabola into place. And the calculations for B and C of this parabola was rather complicated, and I just put the A and get and it put I put the A in the equation, and I got the B and C. If I show you, because this is the B of the degree first. This was the B of the line, and this is the B of the parabola. And I really couldn't figure the whole of it, because it would have been nicer and bigger than this one here. And the C was, I didn't solve it to see it, was bigger. And because of that, I put this, I calculated C in this way. I calculated B here, and I evaluated and created B here and used it here again. Because I didn't have time and energy and intelligence. And then after we find the pattern, like here, if I show you here, if you see, you can see something. You can see there's something going on here. A1 was y2 over this here, and y1 over x2 minus x1 delta x, and then A2, it has an y3 over x3 minus x2 times x3 minus x1, and then minus y2 over x3 minus x2 times x2 minus x1, and then plus y1 over x3 minus x1 times x2 minus x1. And there's a pattern here. And with this pattern, I can, without any further digging into the equations and calculations, I can give you A3, which is here. I didn't calculate A3 at all. I figured it out myself, and it just worked, as the pattern was repeating. And I'm going to show you the pattern. If I didn't draw a straight line here like this one, y equals a0, this way, this is Persian, y equals a0, and a0, we have a0, and y equals 5. Good enough. And when y equals 5, this line doesn't change, and we just need one dot, and knowing that this is a degree zeroth equation to get the idea and the equation. By knowing what actually y equals to, and that y equals just a constant, we can determine this one. And then if we move in further, when we had this line over here, this way, this line, we just need two dots this way. We need, and we have this one. That was A it was equal to a constant, but this is a1 that equals one constant divided by one point. The actually the y2 or the y2, the value of the height of the second point, and then delta x, and this way, totally this way. And if we look at this, we can see we have such a number, or actually it's a number if the dots don't change, over this one, and this delta x should contain an x with the number of that y on the top, like y2 over x2 minus x1 x2, and minus y1 over x2 minus x1. It should contain one of them, and the same is true for a2, which is the a of the parabola, and it is y3 or y3 over 2 delta x's that have and contain an x3, and the delta x should remain the xn minus xn minus 1. It should not we should not write it as x2 minus x3. The bigger number should be the first, and the smaller number, or the smaller n, should get subtracted from the first, the bigger one. And this is the x3 minus x2 times x3 minus x1. It should contain the denominator of every fraction that we add here should contain an x with the same n as the y on the denominator. And same is true here. The y2 over x3 minus x2 times x2 minus x1, and not this one. No, this one, and not this one. We should not put this one in this denominator. And this is the subtraction and addition has its pattern too. The first one, or the nth fraction for the nth the a for a times x to the power n of the polynomial that we want should be positive, and then negative, and then again positive, and then again, if it were continuing, negative, and it should oscillate back and forth. And by this pattern that I discovered myself, and I haven't seen it in the internet before or anywhere else, and no one has taught me to see this pattern here, or no one have told me that. I figured it out myself, and with this pattern, without any actually calculation for a3, I can give it to you. It is y4 or y4 over x4 minus x3, x4 minus x2, x4 minus x1, then minus y3 over x4 minus x3 times x3 minus x2 times x3 minus x1. This has 3, so these subtractions have to have 3 in them, inside them, x3, and this should not contain like x4 minus x1. And then if we continue, it is this way, and then this until the y1. And this worked so far, and if I show you, it's here. And the dot, the fourth dot. So if the parabola, if we can have a parabola with that intercepts with 3 dots, so we can have a cubic equation that contains actually 4 dots, and it is here. It looks like a parabola because it is so close to it, and if I show you, it's not. With a tiny change, we have here a cubic equation. And if this dot here was on this parabola, like this, it wouldn't be a cubic equation, and this A3 would become 0. If I got it well, yes. No, I haven't got it well enough. If I just could do it better and put it on the parabola, it would give me a parabola with 4 dots, because the 4 dots are contained in a parabola. So why should we have a cubic equation? And then if I just put it on animation, it would show its beauty better this way. And this is so amazing because we can do a lot of things with it just the way it is. If we put these equations and calculations to an computer algorithm, we would get higher degree equations, and then we could do many things with it. And this is not the only pattern I figured, but the thing that is upsetting me a little bit is that this pattern is actually very similar to Taylor series. Excuse me, it's so similar to Taylor series, but it's not derivatives. You can have like this function here, like y equals 2 to the x, and then you can align these 4 dots on this equation, and you can have actually an area here that it converges to this function, and you can not exactly and accurately, but rather a little bit with a little bit of uncertainty, you can have the function this way. If I put and align all the points, you can see it. Yes, and that is, and look how close it gets the function. If it was a line, it just got this over here, and it goes far very soon. But if we get closer with 3 dots and parabola, it gets very fine. It gets so fine actually that it gets far a little bit further in the area, actually in the numbers. And if we get the 3rd degree, it actually stays on the function a little bit more, and it doesn't leave the function so soon, and it sticks with it. And but it's not the Taylor series, because the Taylor series is just a circle under one point. You can have one point of a function, and then you can have something like one number this way, one number that way. It can be more efficient in some applications, and this one would be more efficient on other applications. I couldn't find such an application that suits the thing that I discovered yet, but it can be found. And another thing to mention is the pattern that I figured out in the determinants. Like in the 1 by 1 matrix, which is a number, the determinant is just itself. Well, a big discovery. And the determinant of a 2 by 2 matrix is AD minus BC in the 2 by 2 matrix of A, B, and C, D. And same is true for the but we have two rules for getting the determinant out of this 3 by 3 matrix. This one here is the actually Soros rule for getting out the determinant, and no one uses it. I don't know why. If I put it here on the screen, yes, it is here. You actually multiply these three and then these three and then these three and add them together, and you subtract these from it. But Soros made it hard because of this here. We can just multiply here and then these two and this one. The other number after the what was the name of it? If I just know the name, diameter. I think it's called diameter. I don't know anything better now. In the opposite direction of the diameter, if you have two numbers, go to the opposite direction and see the actually the directional, or it was, I just forgot it, but find the number that in its cross-sectional thing, it just adds up to this as becomes the number of the numbers here. Yes, the number of numbers here, and it becomes this way: A, E, I, B, F. We don't need to write them here to figure it out. B, F, and G, this three, and then D, H, C, these two plus this one. And we can, with this pattern, I can guarantee that the fourth 4 by 4 matrix actually will be this way: AFKP plus BGLM plus Chin plus Djo plus D minus the sum of these. It's just like this here. We have 4 on the diagonal, on the diagonal side, and then we have 3 and here, and then we should find the diagonal section that has just one more to give us, with this one, 4 numbers, like B, G, L, and then M, not IN, because it would be 5 of them. And then we would have CH and then IN, and then D, E, G, O, and then we will subtract all the diagonals that are perpendicular to the one that I mentioned, and you can extend it to all the matrices available, like 5 in the degree 5th matrix and the higher degrees matrices, and it will work, and I can guarantee that it will work. And the rest of it is on you, big man, as Rick Sanchez said. And I can call this way of finding the determinant Millard-Soros extended determinant thing, and this was all the explanations that I wanted to give to the Summer of Math, or yes, Summer of Math exposition. And hope you enjoyed the video, and sorry about it getting long. How much? Oh yes, it's so long. Sorry about it being long. And by the way, I just saw the video and I saw that I forgot some other things that I wanted to say. The first one was that I had this I had a quote or something that I wanted to share with you about randomness and what I think about randomness. And in my eyes, randomness is just that when you have to add another term to your formula in order for each term to work, and I've written it better here. Yes, a random pattern is when you should always add another factor or rule to the pattern till infinity, like if you have polynomials and you might be forced to add another factor as you reach any one higher degree. And I replied myself, yes, but the correct way of saying is, randomness is when you should add another factor to your pattern every step forward until infinity in order for it to evaluate the single next term correctly. And this is what I think about randomness and its being, actually. And I wanted to share with you my contact info. I know that in the form you just ask the email and I will write it. It's smilad@gmail.com, and my phone number is, I think it's written down here, 0936 3595 217, and you should not type the O. I wrote the correct phone number for foreigners below, and this is I know you won't call me, but I would be very happy if I receive a call from anyone. And the other thing I forgot to share with you was that the thing I actually mentioned about the determinants was advantageous in the calculation. It has an advantage because it grows actually linear over time, but the way that they are the current way of calculating the determinant, it just grows horribly. I don't know, you can't really go to the 6x6 matrix, and by my way that I introduced to you, I think it's calculatable. I won't guarantee you can nicely fit it in the, but you can actually turn it to an infinite sum for n by n matrix, and so can you for the polynomials that I said. You can have an infinite series for a. You can say a with the nth a, the a of the nth degree polynomial would be y or yn divided by xn minus 1, and then times xn minus 1. You can do a lot of things with that. You can I know you've realized it if you've seen all the details I mentioned in the um, the equations I showed. Um, Hope you enjoyed the video. Uh, sorry about it. That um, Sorry about that. The video gets so long, so dang long. But I apologize for that, and thanks for watching.